The global north, specifically, if you take Europe and America, they've been leading the way in this in terms of the policy and taking specific action in minimizing CO2 emissions and everything. And one of the key solutions to combating climate change and reducing emissions is actually that of vehicle electrification. So if we have a look then at a more closer look at the sub-Saharan African context, we can see that many of the sub-Saharan African countries are actually still in the process of setting up their policies. However, there are a few small cases of electrification, but they often deal with more micro-mobility in sense of two-wheelers and three-wheelers. However, if we want to get the most benefit out of electrification, we need to have a look at the larger systems, such as the paratransit system. So when we deal with electrification, there's two systems at play currently. So the first one is the actual mobility demand. In sub-Saharan Africa, and specifically South Africa, we speak about the paratransit industry or the minibus taxis. And within South Africa, the community strongly relies on these taxis for transporting almost 70% of the commuters on the road. It serves as a livelihood for many people. And a bit of context as well is that there are many fueling stations around South Africa, but not so many charging stations, which we'll get into, which means that fueling is a very quick process when compared to charging, which is a lot slower. Then the second system at play is the actual electrical energy demand. So sub-Saharan Africa is very much characterized by fragile grid networks and an insufficient energy supply, which kind of leads to load shedding as a result, as many of us may know. So when we consider electrification, these two systems that were once independent of one another now become dependent on each other through the whole through charges specifically. And this leads us to two problems that need to be solved in the actual electrification of paratransit. The first one being the taxi is still required to meet the demand of its passengers. This is because of its high reliance in the community. And the second problem is understanding and mitigating the potential grid load that these taxis would have once in operation, because the grid network is significantly fragile. And this then leads to the PhD research question, which is, what are the challenges and opportunities when considering the interdependence between mobility and electrical energy supply in the electrification of the paratransit industry? So how are we going to answer this question? I've identified 4 key objectives into answering this specific question. The first one is to perform a literature survey to establish what has been done in literature already. The second objective is to develop and introduce a methodology to understand for analyzing the viability rate of the electrification process. The second is to develop a simulation tool capable of having this viability rate included in the actual simulation. The fourth objective is to evaluate various factors that could affect such a system in electrification, such as number of charges, charging rate, charging locations, and scheduled versus unscheduled mobility. And lastly is to then derive some conclusions and policy recommendations on what should be considered when the electrification of paratransit eventually goes forth. So this then leads to chapter 2. Chapter 2 was very much published in a variety of articles and conference papers, and is very much summarized in this portion. And it achieves objective 1, which is to perform the literature survey. So if we have a look at some of the literature, when we consider the mobility of electric minibus taxis, it's important to understand how they actually move, because we need to be able to simulate them correctly. So the mobility of the minibus taxis is going to affect their efficiency, which in consequence will affect the electrical energy supply. So we need an accurate way of knowing what their efficiency is. And this is important because the minibus taxis' behavior is substantially different to private vehicles and buses and everything. They have fast acceleration and deceleration procedures, as well as they stop at just random points to drop passengers off or to pick people up. Then the second part to understand is the actual grid impact of electric vehicles. And a lot of literature has covered the fact that electric vehicles do actually place a strain on the electrical grid. And therefore, it's important to understand. However, there's been various investigations into the charging strategies, the different charging powers and charging levels of electric vehicles for charging these electric vehicles. Then if we have a look at existing simulations of mobility and grid, this is just a summarized version of everything. But there's been various studies that have focused on each of these key parameters, including like scheduled versus unscheduled, different charging locations, different EV penetrations, etc. However, in these studies, not all of them are considered, and it's mostly just focused on one specific area. However, what is key from the literature that I found is that the whole process of traveling and charging actually needs to be simulated in order to obtain a more practical prediction of what it will actually look like in the electrification process. Another key point is that the analysis for one country does not actually translate well to another country, and therefore it's important to actually do country-specific simulation. So in doing the literature survey and everything, two research gaps were identified. So the first is that the analysis was largely done for the global north and not for sub-Saharan Africa. And it does, the simulations out there do not accurately represent the unique behaviors and complexities of the paratransit industry that we see in sub-Saharan Africa. So new methodology is therefore required to account for this. The second one is that investigating the integration of grid and mobility is quite a complex task. And some factors are included while others are not, such as number of charges, charger location, charging behavior, etc. And so there needs to be a simulation tool that is capable of simulating electric paratransit. So this then leads to chapter 3, the methodology, and actually developing the framework to simulate electric paratransit. This work was based or published in various articles and conference papers, and it achieves objective 2, which is to develop and introduce a methodology, as well as objective 3, to develop a simulation tool. And I'll be covering the different ways of modeling mobility, as well as the specific framework introduced in this, as well as the experimental setup, and then the metrics used as results. So when we have a look at modeling mobility, there are 3 ways that we can look at modeling mobility. The first way is current mobility, which uses observed mobility patterns from ICE vehicles to assess if the system can transition to electric as is. The second is restructured mobility, which means that we're taking this informal mobility and actually restructuring it to become more of a scheduled transport system similar to buses. And the last one is reform mobility, in which we, instead of simulating current driving patterns, we try and account for driver-based decisions such as range anxiety and all of that within the actual simulation process. So my specific research focused on the current mobility analysis. What happens if we take the system as is and convert it to electric? How does that hold up and stand? And the way we did this was through the introduction of what we call the vehicle day. And it's important to know that the taxi's behavior changes from day to day in the distance and the time that it travels. And this is completely different to buses, which have fixed routes and times in which they travel. And so what we do is with the vehicle day is, instead of just treating everything according to the trips that take place, we rather have a look at the overall day that the vehicle travels. However, because charging actually takes so long, we can't just have the day be a normal calendar day from 12 o'clock until 12 o'clock. We rather shift the vehicle day from 4 o'clock until 4 o'clock of the next day to account for the home charging in the evenings. And so this vehicle day concept is actually able to contain the whole mobility of the taxi within, or the whole movement of the taxi within a given day, instead of just having the normal trip-specific information. However, when we have a look at this further on a more macro level, is we see that there's actually multiple vehicles active on a single day. And because of electrification, these vehicles end up sharing a resource which is the number of charges, which becomes scarce. And so these vehicle days are not entirely independent of one another, but become dependent on each other based on the number of charges at a specific location. And so we term this this grouping of vehicle days that drive on a specific day as a fleet day. And what the fleet day allows us to do is it allows us to actually determine the grid impact that we can expect from these electric minibus taxis. So for the experimental setup, we chose the location of South Africa, and more specifically Stellenbosch, which is at the south of South Africa. And on the right there is just an example of the taxi rank or the depot that was taken for Stellenbosch specifically. So when we come to the data specifically for this, we had received data for 17 minibus taxis that were tracked over a month. So if I just actually go back to the previous one, we set a boundary box around Stellenbosch because we found that a lot of the minibus taxis on the weekends actually end up traveling outside of Stellenbosch to the Eastern Cape, which is another part of South Africa covering around, I think, 1,500 kilometers. And so if we included this in the simulation, it would greatly skew the results. And so we just decided to put a boundary box around Stellenbosch. So with regards to the data that we had from the 17 taxis, if we just included the operational days in terms of the weekdays, as well as the days that excluded the days that the vehicles was not driving, we ended up with a total of 290 vehicle days. Simplifying that further, we ended up with a total of 220 vehicle days. Now, displayed on the screen is actually an example of the mobility that we received, with on the left showing a heat map showing just where the taxi has been the most. And that big red spot in the middle of the map is actually the taxi rank or the depot. And then on the right, we have a route map example of how the taxi actually traveled in a given vehicle day. So this over here outlines the simulation structure of, or the simulation software that I ended up developing. So I made use of EV FleetSim, which is able to determine the micromobility in the sense of secondary data of energy usage of the vehicles. And then I also made use of a similar algorithm used within EV FleetSim to determine when the vehicle had actually stopped. These inputs are then passed to the actual simulation, where we simulate the driving and charging of the vehicles and are able to adjust various variables within the simulation to determine the effects that would have on the overall system. I also introduced the charger association algorithm to manage the resource allocation effectively. And then I made use of an existing battery model with some variations within the simulation. And on the right, you are able to see the various outputs. And some of the outputs, when you have a look at it, the two key ones is the grid power measured in kilowatts, as well as the viability rate in percentage, which just means how viable is the transition going to be? How many minibus taxis will be able to be converted to electric in terms of a percentage? Then some other smaller metrics that we're able to determine is distances in how far they can travel in a given vehicle day in terms of kilometers, as well as the charger utilization in percentage, number of charges per vehicle as well. So this then leads us to the results. Now, the results were published in mainly two journals, that being the Energy for Sustainable Development Journal, as well as the African Transport Studies Journal. And this work completes objective 4, which is to evaluate various factors of the system. So the next slide, I'm going to show you actually what the simulation looks like. But before that, it might go very quick, but I want you to just notice that the SOC of the vehicle starts at 100%. And so what we have over here is the various vehicles that are actually driving and charging on a given vehicle day or on a given fleet day, with each line representing a different vehicle. Now, the downslopes is the vehicle driving, with the upslopes being the vehicle charging. And what is shown over here is actually the SOC of the battery throughout each iteration. Now, important to notice in here is if you have a look at the closer to the 100% mark, you'll see that the battery or the SOC actually decreases slowly, and that's because of the battery model, and that's typically what we see in a practical example of charging. And you'll notice that the end SOC of the vehicle becomes the start SOC of the vehicle for the next day. And this is important because what this means is that we do not need to do a random distribution of SOC to determine if the vehicle is viable or not, but we can just iterate over the vehicle day consistently. And if it's able to still meet that demand consistently, that vehicle would then become viable. So that's when we get the concept of steady state within the simulation, which just means that the end SOC is the same as the start SOC of the vehicle. And I'm sure you noticed that some of the vehicle days actually went to 0. And in those scenarios that the vehicle SOC went to 0, that vehicle day would be considered unsuccessful, with the vehicle days that reach steady state being considered successful. So then if we have a look at results, we tested various different metrics. So the two rows, we have depot only charging being the top row, and the bottom row being depot and home charging included. Then if we have a look at the columns, we varied the charging rate at the depot being 7.2 kilowatt depot charging, 22 kilowatt depot charging, and 50 kilowatt depot charging. It's important to note that for home charging, we chose a consistent value of 7.2 kilowatt charging at home. So you can notice, I'm not sure if you can see, but actually in the actual simulation, the number of charges increases, and then the viability rate, shown in the percentage, actually increases as well until it reaches a specific point. And this is what we determine as the maximum ability that is actually able to be achieved. So to summarize all of these nice looking graphs, we get to these viability rates over here. Are you guys, is it not showing? There we go, it's a bit slow. Okay. There we go. So we can see where maximum ability is achieved, that for a depot only charging scenario at 7.2 kilowatts, we actually only receive a viability rate of 11%, which is pretty shocking, to be honest. Then if we increase that substantially further to 50 kilowatt depot charging and have 7.2 kilowatt home charging, that increases to 86% as the best case scenario. But even then, that is still not 100% viable. So I also went and did another test in the case of what happens if we do home only charging, and we can see that in the home only charging at lower charging rates, we were actually able to receive a 34% increase in the viability rate. However, for the faster charging, home charging doesn't make sense. But the most optimal solution will most likely be a combination of both depot and home charging. Now, one of the other outputs of the simulation is the distances, like I said, and this is just an example of what the distances actually looks like, where the viable vehicle days is shown in orange and the unviable vehicle days shown in blue. So if we summarize all of this, these are the distances that is able to be covered by the vehicles. And again, for the home only scenario over here. So just to put these numbers in context, private vehicles travel around 40 kilometers a day, with these minibus taxis traveling almost 5 times more. So from the simulation, we get 2 types of distances. The first is the distance that can be traveled in a vehicle day given sufficient charging, and the other one is the limit of the actual battery being 140 kilometers that a vehicle can travel in a single trip without having needed to recharge. Then if we have a look at the grid impact, we can see here the maximum for the specific fleet days for increasing number of charges. And I just want to draw your attention to the fact that We see two peaks. The first one is in the morning peak, which occurs directly after the taxis have dropped off people at work between the hours of 8 and 10, and the second peak between the hours of 7 and 10 in the evening as well, when home charging is included. Interestingly enough, home charging actually substantially reduces the morning peak, with the morning peak also potentially being able to be covered by solar as well. Then quickly, if we just have a look at the current actual electrical grid situation in South Africa, for increasing number of EVs, we see a pretty alarming scenario. So for the actual scenario in South Africa, we would not be able to have any electric vehicles, electric minibus taxis on the road. However, if we take the ideal scenario in the case that the installed capacity is the actual capacity of South Africa, we see a very different story in that slow and medium charging is pretty substantial. However, fast charging, seen by the brown and orange, will actually quite substantially negatively affect the grid. So this was an interesting, another side note that we tested what happens if we increase the battery capacity, and we found that actually increasing the battery capacity does not provide as much benefit as including home charging. So rather, instead of trying to get more out of the battery, we should rather install home chargers instead. So one of the key discoveries of the first part is that the mobility of the taxis would need to change in order to receive higher viability rates. And so that led us to chapter 5, which is the restructured mobility. What happens if we do the impossible and actually change the vehicle's behavior to that of a more scheduled nature? This was published in the Journal of Cleaner Productions and still continues to meet objective number 4. With this introduction, we added to the methodology and the framework through the use of a vehicle trip. And now what the vehicle trip is we're able to ascertain the perceived passenger demand of the taxis based on how long they stopped at a specific location, with the assumption being that if the taxis have stopped, there's no passengers in it, meaning that they're not actually driving. And so we're able to term this mobility between these stop locations as the vehicle trip. Another interesting thing that we introduced here is the concept of a mixed fleet, where we take the vehicle day and instead of representing it as a viability rate, we have a look at if the vehicle day was successful, that vehicle becomes electric. If it was unsuccessful, that vehicle becomes an ICE vehicle then. So when we have a look at the experimental data, I made use of the same data set in the previous chapter, and these are the various stop locations. You can see actually quite a few stop locations, and I just did a kernel distribution with a radius of around 150 meters to get less number of points, but still accurate representation. And this resulted in about 1,007 vehicle trips from the data set. Then if we have a look at the results, this actually shows the current pattern versus the scheduled scenario where we've restructured it. And you can notice that in the restructuring, we actually make use of far less ICE vehicles and far fewer vehicles in the fleet as well. The same kind of pattern is seen in the number of chargers, where far fewer chargers are needed in the scheduled scenario, with the current mobility requiring substantially more charges. Then on the distances, I just want to draw attention to the right there with the EV and ICE combination, and we can see that the scheduled scenario actually has an increase in distances, and this is because we have what is called dead bands introduced when the vehicle travels between depots or between locations to pick up people. So distances are actually added to that. Then again, we can have a look at the grid impact, with blue being the current and green being the scheduled. You'll notice that the green or the scheduled scenario is actually pretty flat and substantially less than the current mobility. However, it is spread out throughout the day. Then if we have a look at the actual fleet sizes for the scenario that we analyze, we can see that the restructured mobility makes use of fewer vehicles and more electric vehicles as well. So it has a higher system performance. Then another scenario that we found during the research is actually this concept of a just energy transition introduced in these policies in the terms of how just or how easy access do people have to the benefits of electrification. And so this work was published in the Energy Research and Social Science Journal, and it still continues to evaluate objective number 4. So just a bit of background. So a just transition, like I said, is a guiding principle in climate change policies. But how do we actually go about that from the driver's perspective or for the vehicle's perspective in a just energy transition? And the way that we do that is through the vehicle day classification. So the first way is we characterize the vehicle day according to home type or according to home location. And the second is by the type of travel that it does, if it travels between cities or within a city. So, for example, intra would be from the green box to the blue box, and inter would be just within the green box. So if we have a look at the data sets that we used, we actually see two groups of people that are identified in the data, with group A and group B showing the home locations in the heat maps. Now, if we draw that to actually a real map, we can see over here, red is given by, I think, group A, and group B is given by blue over there in Kayamandi. So just to show you what that actually looks like, if we have a look at the historical background, group A, being those in Cluttersville in red, are actually people of lower middle income, and it's a historically colored community. Whereas if we look at group B, which is Kayamandi, these are people of lower income and historically black community as well. So just some of the data that we found is that we found that group B actually travels a lot further than group A. And this is because they perform a lot more intercity than intra-city trips, meaning they travel from Stellenbosch to Somerset or Stellenbosch to Bellville, outside of municipality jurisdictions. We also found that group B actually has substantially higher energy consumption than group A, and this is because of the higher traveling speed, and they're traveling more on highways as well. So just some more stats. Group A has 86% is done through intercity trips, with Group B doing 84% of intercity trips. So when we have a look at the viability rate, we see that Group A has a viability rate of 53% for the depot-only charging scenario, but this is increased to 82% if we increase home charging. However, Group B is substantially lower, only having a 2% viability rate for the depot scenario and 32% for the home charging scenario. And the same can be said for intracity and intercity. So it just shows that intracity trips is more viable for electric vehicles than intercity trips. As well, from that, you can see that the electrification transition would affect one group or be better for one group than the other group. Then again, we can model the grid impact. Just something of note here is the fact that Group B, the people in Kayamandi, actually get home later and start charging later by the purple line on the right when considered to the red line. Finally, to summarize everything up and having a look at the conclusions that we're able to draw from all of this research, there is a couple of conclusions. With the fact that mobility needs to change in order to receive higher viability rates, home charging is a serious consideration. Distances, there's two types of distances: the grid impact we can expect during the day, as well as the fact that electrification can benefit one group and conversely affect another group. Finally, just to highlight the original contributions of this research, and classify the ways of simulating electric mobility for sub-Saharan Africa to the current restructure and reform mobility, presented a methodology for assessing the viability rate of an electric transition through the vehicle day and fleet day concepts, as well as developed simulation software for the viability rate. We were able to obtain the expected grid impact, as well as expanding on the methodology to bridge the gap between current mobility and restructured mobility. Introduced the concept of mixed fleet as a viable solution to electrification, as well as investigated the justness of the electric transition. Finally, some future research that needs to happen. A deeper level grid impact analysis should be performed. My research very much focused on a high level, but you can go in frequency analysis, voltage analysis, transformer impacts and everything, as well as more offsets of the grid impact with the use of stationary batteries and solar panels, what the effect of time of use charging will have, as well as adapting driver behavior in terms of range anxiety, as well as to perform an analysis on a larger data set as well. Thank you.
Okay, thank you very much. Took a whole vehicle down.